All right, so the recording has started. So thank you so much for joining today, everyone. I'll quickly introduce myself and then I'll introduce our speaker. I am Pooja Kulkarni. I'm the founder and director of Stats Club. Stats Club is an open science initiative which works towards making statistics and R more accessible. And today we are very thrilled to be collaborating with Dr. Sacha Epskamp for this workshop on CFA and structural equation modeling in R. Dr. Sacha Epskamp is an associate professor at the National University of Singapore in the Department of Psychology. His research interests include multivariate data modeling, longitudinal analysis, psychometrics, network modeling, and complexity science. He has taught many courses on psychometrics methods and data science. Dr. Epskamp has been actively contributing towards open science and has made many of his lectures and tutorials freely available on his website and on YouTube. We are very honored to have him as a speaker today. And without further ado, I invite Dr. Epskamp to begin today's workshop.
Thank you very much for the introduction, and thank you very much for inviting me. It's a great initiative, what I hear, so it's really nice that you're organizing this. Everybody can hear me just fine?
Yeah, we can hear
All
you.
right, okay. I will start sharing my screen. Then I have to search for the theme buttons that allows me to do that. There we go. Hmm. Let me see if I can. How does this work?
Yeah, we can see your screen and
Also
you.
me?
Yes.
Okay, so maybe I do it like this, but I don't see you here, so I probably won't see it if someone have any question.
I can let you know
Okay,
in
yeah,
case there are questions. So I'll let you know.
yeah,
I think most of the questions maybe we can take towards the end. However, if there are questions that need like immediate answers, so that then I can maybe let ask you immediately.
sure, yeah. So
Yeah.
if you can let me know if there's a question in chat or another
Yeah.
question, then that would be great because I can't see it.
Yeah. 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 I'll
Right.
let you know.
All right, welcome everybody to this workshop on confirmatory effect analysis and structural equation modeling. So I've been asked to give an introduction to this and how to do it in R. Structural equation modeling is a quite big field, a quite big area of modeling. So I won't have time to really delve into all the details of SEM in only 2 hours because it's quite big. I usually teach a course on this. This takes 12 weeks where I really delve into all the details. So I'm just going to give you a basic introduction now, but hopefully by the end of the workshop you'll be able to do something and to run some analysis in R, especially a CFA analysis, which is a subset of structural equation modeling, so a confirmatory effect analysis, which is a special case of structural equation modeling. Structural equation modeling is a bit more advanced. It includes some structural effects as well, which I'll show. But the code is the same. If you do SEM or CFA, it doesn't matter that much. So if you know how to run a CFA model, then taking the step towards a SEM model is not that hard. Now, I will show you how to use the R package Latent. I did not make Latent. Latent is made by Yves Rossel in Ghent in Belgium. I made another SEM package called Psychometrics, which you can use for structural equation modeling as well. I chose not to teach that package because Latent is actually better for structural equation modeling. My package can be used for some other things like longitudinal modeling or network modeling. So yeah, I think Latent is actually a really good package. So I just wanted to give an introduction to that. I teach on structural equation modeling. So basically the slides is based on those lectures. On my YouTube channel, I actually have the whole course available for free as well. So if you're interested in learning more, then on my YouTube channel you can find detailed lectures on CFA and structural equation modeling. Okay, so what is structural equation modeling, or SEM, as we abbreviate it? So structural equation modeling is a modeling framework that is very, very generic, and it allows us to do a lot of interesting models and answer a lot of interesting questions. In essence, it's a modeling framework for multivariate models that aims to explain how variables correlate with each other or covary with each other. So the data always looks like a set of observed variables. Let's say we have a data set where we have a column indicating some variable, something we measure. In the case of psychology, usually questions like, how do you feel right now? We could think of yourself as a person that is adventurous. Are you experiencing depressed mood? Things like that. And the rows are typically cases, usually for us people, but they could also be time points, or for example, countries or other types of cases, observations that you might have. Structural equation modeling, but these are variables. Structural equation modeling aims to explain why some variables correlate and covary. That's really the main goal behind it. And it does so by using latent variable models, where we introduce latent entities to try to measure something. So we're trying to explain. We don't have to use latent variables, but that's usually what we do, especially in factor analysis. We try to explain why items correlate using latent variables that we assume underlie the items, things we cannot directly observe, but we're interested in. So constructs like depression or neuroticism or extroversion, for example. It allows you to do very advanced multivariate causal theories, which is nice. But even more, it allows you for a group comparison, which is a very strong aspect of SEM that I won't talk about today. But it allows you to test, for example, if a test is fair in two groups, or if there is heterogeneity across those groups in the latent variable, or if there's if you cannot say that because the test is not fair, for example. Basically, if you really learn SEM, you can replace things like t-tests, ANOVA, regression with structural equation modeling and do it in a better way, because we can model latent variables and constructs directly at the latent level without the need to take, for example, a sum score. In psychology, that's what we do quite often. We might take, for example, the sum score of 10 items and then do a test, like a regression or t-test, to see if that differs from something or the groups differ or something like that. In structural equation modeling, we don't have to take a sum score. We can actually model the latent construct we're interested in directly. And the models look a bit like this. You'll see a lot of Greek letters. I will introduce some of these Greek letters, but yeah, you can also ignore them. The arrows are more important. You see here a latent variable, something like depression, neuroticism, for example. This might mean they're correlated with each other. So we assume that there's a correlation between depression and neuroticism. There's some variance. That means that they differ across the population. People have different neuroticism levels, different extroversion levels. Like my neuroticism might be different than someone else's. And we assume that these latent constructs cause underlying indicators. And we can model something like this. This is a CFA model, or a confirmatory effect analysis model. This one here, which is the model that I'll show today, how to analyze this and how to estimate this. And it can lead to interesting conclusions. So for example, you can conclude that underlying our data set of 6 items, these are observed indicators, 6 items, like questions like how do you feel, underlying that, there could be 2 latent constructs that are causing the covariation. And you can test how strongly they correlate, how strongly are they related to each other, which is a very powerful thing. Now, taking it one step further, in structural equation modeling, this is something I won't directly talk about today, but it basically follows the same logic. you can test actual causal effects between these latent constructs. And that's really powerful. That means that you can test, for example, if depression causes neuroticism, or neuroticism causes depression, or things like that. And it can get like more advanced. So for example, here we have like a very advanced model where we have two independent variables, or exogenous variables as we call them, and we see how these cause things like task orientation, ego orientation, and that eventually causes something we observe, exercise adherence, and all these things are indicated with multiple indicators. There's measurement error, that's what this thing says. So it's a very advanced model, this, but it's something we can test in social equation modeling. Okay, are there any questions so far?
No, so
No,
far I
okay.
don't see anything in
All
chat.
right, good. All right. So before we start doing this, I want to take a bit of step back and think a bit about measurement. So in psychology, we usually are interested in constructs like neuroticism, or your concentration, or political conservatism, for example, things like that. But how do you actually measure these things? Because quite a lot of these things we can't directly observe in the real world. Like we can't really measure neuroticism directly. It's not like we can measure it in the brain or anything. And so how do we measure something? Right. So if we make it a bit more concrete, we can think about something like temperature. How do you measure temperature? The temperature is also something that is, can we directly observe temperature? Not really, right? So temperature is a physical aspect of the world right here. It's not like we can really see it or feel it, right? We can only really try to measure it by looking at things that we assume are caused by temperature. Right? So for example, we look at the thermometer. Now this idea works because there is something called temperature, and we assume that temperature is causing the level of the thermometer. Now in this case, we understand quite well why that's the case, right? This is like quicksilver or something like that. It expands. There's a reason why it works, right? So we don't have to assume, but still, we can measure temperature with a thermometer because we know that temperature is causing the variation on this thermometer. So we know that that's caused, and we know that the thermometer is relatively precise. There's not that much measurement error. So because of that, we can use it to measure temperature. Now we can summarize this idea that we have something latent, like some unobserved temperature, which we don't really know, right? But it causes something that we can see, observing, but we can assume that there's also some certain level of error still. Now, this is what we call a path diagram, and as you saw before, like here, we use them quite a lot in social equation modeling. And they're quite useful because they allow us to summarize a causal hypothesis or a causal idea. So how does this work? You see here a circle, like a sun, in this case, but just normally just a circle. And here you see another circle, actually. The circles represent things that are unobserved. The stuff we don't observe, so things we don't have the actual data from. In this case, there are two unobserved things. We have the actual temperature, and we have the residual, the error on our measurement. The square things, in this case rectangular, but usually square, are variables we observe. So these are, if you have our data, our columns in the dataset. Then we have also the arrows. We have two types of arrows here. A unidirectional link, so an arrow. This is what we can interpret as a causal effect. You can also interpret it as a regression. But you can take a stronger interpretation, and there's quite a lot to say about that. So I won't do that here, but there's like you can discuss this in way more detail. You can take a cost interpretation here. You can assume that this arrow means that this causes that. I think you kind of have to take a cost interpretation, because otherwise, why are you measuring, including error, if you don't assume this causes things? So I will assume these are causal, but yeah, some people disagree and they say there's more regressions and you don't have to take cost interpretation. They'll say, okay, this is a causal effect, and these double-sided arrows here, those indicate variances or covariances. So that's something very different. That tells me temperature varies, which means that if I measure temperature on different days, I would get different values. The error will be different as well. So this thermometer, then we have to assume that it will not measure temperature precisely. It will have some misfit on there, some error, but that error is also random and will differ from day to day as well. That's what these double-sided arrows tell me. Okay, so now if we get rid of suns and thermometers and we include more Greek letters, if we assume that all observed variables are normally distributed, which is something I'm going to assume, and something we assume in structural equation modeling because it makes the math work out, and all cost effects are linear. So we assume that there's a linear effect here, which really looks like this. So we have a latent variable, temperature, we have an observed variable, and there's a line. Right? So for some level of the latent variable, we have some level of the observed variable. That's the idea. If we assume all that, and I'll assume that means are 0. We don't have to do that. So I assume that we centered the data here. We took out the mean. That's a very small detail. It's not that important because actually we can get around this, but it makes the math just a bit nicer. And I want to include some maths on the slides to really show what's happening. Now this path diagram encodes a causal equation, which is this equation here. And that means that basically for this variable, this y, which we call it the dependent variable or the outcome variable, the thing we're interested in measuring, we basically just sum all the incoming arrows. We multiply the effect on the path times the variable. So we have here lambda times eta plus epsilon. And these are this is the variance of the latent variable, this is the variance of the residual. Yeah, there's quite a lot of things happening here, quite a lot of Greek letters as well. So I'll take it one step at a time. Here we have our indicator, our column in the data. We assume that indicator is a linear combination of a vector loading times some latent variable that we don't know, like some latent temperature, plus error. And now because I set the means are 0, there's no intercept here. So normally you'd have an intercept term, right? You could call it B0 in regression, but let's call it like tau, for example. But because we assume the means are 0, that drops out, so it becomes a bit simpler. Right? And so this is very similar to a normal regression model where you have B0 plus B1 times X plus error. The only difference is that X is now not observed. So that's why we call it eta. And these subscripts they are because you can have multiple latent variables, things like that. All right. Usually we'll write this in matrix terms, which is a bit easier. So here I have y equals effect loading times the latent variable plus residual. This is the same expression, but in matrix terms. If you know matrix algebra, then you can work that out. Like this is now a matrix with multiple vector loadings. This is a vector with multiple latent variables. This is a set of multiple items. If you don't know matrix algebra, then this is not that important. I just wanted to include this to show what's really happening. Because this expression is this expression that's actually quite important. Y, a set of variables, equals a regression on the set of latent variables plus error. Really meaning we have a latent variable, we have observed variable, we have a line indicating for some level of the latent variable, we assume some level of the observed variable. And we have quite a lot of Greek letters here. We have y, well the y is not a Greek letter, but eta is the latent variable variance, latent variable, sorry. Lambda is the vector loadings. Epsilon is the residual variance. The residual. And then the variance of the latent variable we call psi, and the variance of the residual we call theta. Like again, a lot of Greek letters. If you really want to learn more about SEM, it is useful to just study the Greek alphabet, because these letters are used quite a lot in these equations. And yeah, it's quite useful if you can think about these letters in terms of their actual name. When I studied SEM the first time, I read this as like upside down y, and at some point you're thinking y equals upside down y times weird n, and yeah, it gets a bit hard. So it's easy to just study the Greek alphabet at that point. So that's why I included this slide as well, so you can refer to that. All right. Are there any questions so far?
I don't see anything in the chat.
All right. Good. I'll just come back sometimes to make sure that maybe I lost my internet and I'm not talking for like to my screen. I don't know. So I'm just gonna come back sometime to ask.
I think they will definitely like put in chat if anybody has any questions, and we will have time towards the end as well for them to unmute.
All right. Okay. All right. So this is the main thing we actually do in SEM. We have this model here, which we call a measurement model, where we are trying to explain why set of observed variables from the latent variable. All right. So we have an idea, right? We have something latent we want to measure. So our hypotheses are on this level, right, in temperature, not on the thermometer. Right? So our hypotheses are not. If we are interested in, for example, comparing two groups on their neuroticism level, we are not interested in their difference on an item. We're interested in their latent level and seeing how they differ at the latent level. So ideally, we measure the latent variable and get a number for that, right? So we have data only for y. Ideally, we would get a latent variable, eta, right? Which normally do with a sum score, but that's quite problematic because it doesn't take measurement error into account. So ideally we would do that, but the problem is, and that's an interesting thing in psychometrics in general, so psychometrics is the field of measuring psychological constructs, really the field of that is really concentrated on measuring latent variables. An interesting thing in psychometrics is that we want to get a value for the latent variable, but actually we can't. And that is because it is impossible statistically to reliably estimate both the parameters and the latent variables. What does that mean? Right, let's go to this slide here. I can't remove my annotations, it's okay. I'll draw it here again. Y equals lambda eta I plus epsilon I. All right. So what does this I mean? This I means the subject. Right. So if we have 10 subjects in our data, right? So our data would be 10 rows. If we have 10 subjects in our data, we would have 10 times a y variable or a set of y variables, 10 times a latent variable, 10 times residual. We also have these parameters that we need to estimate, these lambdas, for example, here, and also these, right? But in this case, it would only be the lambdas, but we're going to get to these later. Now, in statistics, we really want to be able to asymptotically get somewhere. Like we want to be able to estimate a parameter, and we want to know that if we add infinite amount of data, we get that parameter back. The problem is here we cannot do that, because if we would add more data until we get infinite amount of data, we also have an infinite amount of latent variables to estimate. So we're never going to converge on something. Every time we add a row, we make our life more complicated because we have to add latent variable. Every time we add a variable, we make our life more complicated also because we have to add a residual variable, and we have to add a parameter effect loading, for example, for that variable. So if we add rows, data, we make our life complicated. If we add columns, we make our life complicated. That's a pretty problematic thing. That's a really problematic thing in psychometrics. We have to add estimate parameters, latent variables. We cannot do it jointly. We cannot do it at the same time. So an interesting thing is that the first thing we actually do in psychometrics, in any model, in structural equation modeling, but also in item response theory models, if you know about that, other models as well that use latent variable models. For example, also multi-level models, where multi-level models are also a latent variable model. The first thing we do is we get rid of the latent variable. Now that sounds really weird because that's the thing we were interested in, right? So what do we do? We integrate out the latent variable, for example, or that's what we do here. We make use of covariance modeling, which basically means that we look at the marginal distribution after taking into account the latent variable. So that means we, instead of trying to estimate the latent variable, we instead will try to estimate the variances and look at how does the variance of the latent variable impact the variance of our observed data set. By doing that, we reduce our problem because now we only have to estimate the distribution of the latent variable, maybe the variance and later the mean if you do like mean structure modeling, but mostly the variance and how it relates to other things. We can do that because we have multiple indicators, multiple observed variables, and assuming a structure like one common cause, for example, has a very strong imposes a set of strong constraints on the covariance structure, which is a nice thing. So that means we would not get a latent variable anymore per person. We actually don't get these latent variables, these measures. Now, isn't that a problem? Because that's what you want, right? Yes and no, not necessarily. And that's a very interesting thing. For many hypotheses, it might not be a problem. For example, let's say if you're interested in this hypothesis here, that these two constructs are correlated. Okay, we can take a sum score of a scale here, sum score of a scale there, and do a Pearson correlation, but then we don't take the residual variance into account. We assume that all items are equally good indicators of latent variables and some other problems. We can also directly model their implication on the covariance, which means that we look at how do these items correlate, and assuming that this is the underlying structure, that means that the correlations between this set of items here and this set of items here should all go through this parameter, and we can actually estimate that. And we can get a confidence interval on it, and a standard error, and a significance value, and things like that. So that means that by covariance modeling, by using covariance modeling, we didn't need to estimate some scores and correlate. Then we could actually already estimate this covariance directly, and that might be the thing we have hypothesis on. If you have this castle hypothesis, we can estimate these regression coefficients directly. We don't need to first sum these and create these actual factor scores in our data. We can model this structure directly and get these parameters, and then that might be what we have a null hypothesis on. If you do multi-group SAM modeling, which I don't talk about today, we can do group comparison like t-tests at the latent level without the need of ever having to estimate or measure the latent variable. If you want to do a test, for example, to see if in a group the latent variable is above a certain threshold that you might be interested in, then you can also do that. So for many cases, we won't actually need to get the latent variables. Now, if you really want proxies of latent variables, that's called factor scores, You can get them. There's just a function in R called vector scores. It can be extrapolated. But they're still estimates, so they're not great. They're still estimates of the latent variable. They're not the actual true latent variables. We don't actually need them mostly. So if you do SEM modeling, most people won't use them, but they can be obtained. I won't talk about that today because I just want to give an idea about circular equation modeling, but yeah, it is possible to obtain them. Okay, so let's take a look at, are there any questions so far, by the way? No questions yet?
No, not yet.
Okay, great.
Someone just put something in chat. When we use variance, technically we are not directly measuring a latent variable.
Yeah, so when we are looking at the variance, we are not actually measuring the latent variable because we don't get the values per person of the latent variable. We just get an estimate of the variance. Or rather the distribution and what it implies to have one latent variable underlying the data. That's the idea. All right, so what we're going to do is we're not trying to model this. We're actually looking at what variance does this model and what covariance does this model imply, and we try to model that. Now, to get that, we can use something called variance covariance modeling or covariance modeling or covariance algebra. It's a set of rules. For example, the covariance of A plus B with C equals the covariance of A with C plus the covariance of B with C. Oh, that's terrible. Set of rules like that. I won't go into detail about it now, but the set of rules allows us to go from one expression like this here on the left and see what does that imply in terms of variances. Now, again, this is something I actually have on YouTube, a detailed explanation on. So if you're interested in that, you can look at it up in our YouTube channel. But this model here, Y is caused by eta lambda 1, 1. It's called lambda 1, 1 because it's the first row and the first column of a bigger matrix lambda, which is the matrix I use here. So lambda 1, 1 times eta 1, so the first element of eta, plus epsilon. If that's true, and these things are not correlated with each other, then the variance of Y should take this form. The square of this vector loading times this vector variance plus the residual variance. And these are these things here, these parameters here. Okay, and we can use that, for example, to get an idea about how much variance is explained by the latent variable. That could be interesting to see if it's a good indicator, things like that. This thing basically, this vector loading says that something is a good indicator or not. The stronger it is, the better an indicator, because the more a latent variable impacts the latent an observed variable. This thing here, the residual variance, actually tells us if it's a bad indicator. If you have a lot of residual variance, it means that there's a lot of error in our measurement and it's not that well indicated by the latent variable. So we can do that. Get an expression like this. And then we can use that, for example, for that. Now what we're going to do is we're going to use these variances, these expressions with variances, to estimate parameters. Well, you won't do that. You're just going to use the software because the software does it for you. But this is the principle that analyzes it. So we have observed variances and covariances, meaning that we observe in our data, for example, in this case, the variance of y1. In this case, our data is only one variable, right? It's called y1. And what we can do is we can take the mean, but the means are 0, or we assume the means are 0, or we're not modeling them. We can also take the variance. We can just look at that, right? So our data gives a variance estimate, which is like something that we have. We can look at. It's also data that we have. So that's known. That's this thing. We know that, the variance. And we match that to the parameters, some expression of the parameters, so that we don't have to estimate these latent variables themselves. That's the main idea. Okay, that's nice. But this expression, so we know this, right? So this is known, this is variance, and these are not known. Right? This expression is not solvable. And so basically, this reads like x equals a times b, b plus c, right? Where x is unknown, x is known, but a and b and c are unknown, and then we try to solve it. We can't do that because we have only one piece of information that's known, x, and we have 3 pieces of information not known. That's already a problem. But the main problem also is here, right? So we have a vector loading times, or vector loading square, but that doesn't really matter that much, times the vector variance. These things can cancel each other out. And that means that if I can make my vector loading arbitrarily big and just make my vector variance smaller to get the same product, right? So this is basically a times b, a is vector loading squared, b is the vector variance. If I make a 2 times bigger and I divide b by 2, it's the same result. Right? So there's no way I can ever solve this because this will give me the same result. So that's the first problem. And that's the problem of scaling. Now the problem of scaling is that we know our observed variables, they're on some scale, there's some unit, but we don't know the unit of the latent variable. Which means that because it's latent, it's not observed, right? We can't see it. So for example, temperature, sure, I have a thermometer and it's in Celsius, right? Sure, okay. That's the unit of the thermometer. But I can have another thermometer and it's in Fahrenheit. If I use both thermometers, I'm measuring the same thing as this temperature. The temperature in the real world, it doesn't have a unit or anything, right? So I can define it in any way. And then I can find some way in which it translates to my thermometer. So the first thing we need to do is actually define the unit of the latent variable. Well, basically, we need to make sure that this thing doesn't scale without bound. We need to make sure that we identify it. So we need to identify both the mean and the variance of the latent variable somehow. Now, how do we do that? The mean we just usually assume is 0, so we just need to set some value. Like we don't know that, because we don't know the mean temperature, so we need to assume some value. And that's because we can then add an intercept. That's not that important, I'm not talking about that today because I'm assuming things are centered. The variance we need to somehow define. Now how do we do that? We have here this thing here, which is problematic, and this thing here. We cannot estimate both, in this case, with one indicator. So the simple idea is that we need to set one of these parameters to 1. Or to some other value, but usually we do 1. Yeah, it could be like, for example, if this is IQ, then actually you would set this to 15 squared because the standard deviation is 15. But normally you would set it to 1, which is just some value. So what does it mean? We either set this to 1 and we don't estimate it. We make sure that we just assume it's known, or we set this to 1. It doesn't matter which one you do. Usually it's the same effect. There's some small details, but they're not really that important. If I set this to 1, then this thing is a standard normal distribution, which is easier to interpret. But rather, if I set this to 1, then the unit of the latent variable is the same as the unit of the first indicator, which is also easy to interpret. Okay, so I set this parameter to 1, this vector loading to 1. Makes our life easier, right? So we don't have this problem anymore that we're multiplying this with something else. That's good. But then I'm still left with a problem. So here I have my expression now that I'm trying to use, where I have 1 known and 2 unknowns. Right. So this has the form x equals a plus b, where I know x and I want to estimate a and b. I cannot do that because I can set any a to any value and then set b just to whatever I need to set it, right? So if x is 5, for example, I can just arbitrarily set, okay, a is 1 and b is 4, right? Or a is 2 and b is 3. Like there are infinite amount of combinations I can use to get this. So that's problem 2. In this case, we cannot do this because we have 2 unknowns and 1 known value. We cannot solve that equation. So yeah, that is also problematic. So what do we do to get around that? Well, we need to add information, right? So we need to make sure we get to an area where we have more things that we know in our data than we don't know. Now, in this case, because we're talking about variances, we can't just add people, right? So let's say we have a data set. This is the number of people that we have, I, right? It goes to n. The more people we add, it doesn't actually add data points. It doesn't actually add, it just adds a more precise estimate of the variance, but it's still only one variance that we have. So instead, we need to add variables, because that will give us more variances and covariance that we can use as data. So that brings me to degrees of freedom, which is a very important topic in statistics, and I assume all of you will probably have encountered it at some point in your life already. Degrees of freedom indicate how many free elements there are in something we try to estimate, and it's always defined as the number of observations, A, minus the number of parameters, B. So if you need to estimate a certain number of parameters, we need to make sure that this degree of freedom is at least 0. That's the main idea. Now you might have seen this in a regression model where we have, let's say, 1, 2, 3, 4 data points. We have a line. This line has 2 parameters, a b0 and a b1. All right, so the slope and the intercept. We have 4 data points, 2 parameters, then we get degrees of freedom of 2. That's what we normally get in the regression model, but now we're not doing this. We're not looking at the data anymore. We are not looking at individual data points. We're looking at variances and covariances. So we're trying to match our parameters to the variances and covariances. So the number of observations now is not n, not the sample size. It is the number of variances and covariances we have in our data. Let's say if you have a 3x3 covariance matrix we're trying to estimate, then how many unique elements do we have? We have 1, 2, 3, 4, 5, 6. 3 variances on the diagonal and 3 covariances. And the other part is symmetrical. Right? So that means that the covariance between variable 1 and 2 is the same as covariance between variable 2 and 1. Right, so if you have 3 variables, we would have a variance of variable 1, variance of variable 2, variance of variable 3, a covariance between variable 1 and 2, a covariance between variable 1 and 3, and a covariance between variable 2 and 3, which is this expression here, how you can calculate that. Now, at some point, if we add more variables, if our model is parsimonious enough, we're going to get more observations than parameters. And that's a great thing, because then we can do statistics, right? Which is what we want to do in life, in general. Okay, so here in this model, how many observations do we have? I have only one observed variable that leads to only one variance. Okay, so one variance that I observe, but I have 2 parameters after scaling, right? So this one is no longer parameters, it's fixed, that's nice. We have 2 parameters here. So we have here 1 and 2. So we have 1 minus 2 equals minus 1. That's a terrible thing. Degrees of freedom of minus 1. It means that the model is not identified. We cannot do anything. We cannot estimate its model. We can get any number of combinations, like an infinite amount of combinations for these parameters, so it's a completely uninformative model. Okay, so let's now try to add variables. So now I add a second indicator. So now I add a second indicator in a data set. So now I have a model, a data, we have y1 and y2, two variables. I have to set one vector loading to 1 for scaling. I don't have to set the other one to 1 because this vector variance is already scaled in the expression for this first variable. It means that variance this equals this vector variance plus this residual. Because of that, it cannot arbitrarily become big because then that wouldn't fit anymore. So that's a great thing because it means we can actually estimate the second vector loading. So basically that thing is relative towards the first one. If this is higher than 1, it means it's a better indicator. If it's lower than 1, it means it's the worst indicator. If the scale is the same for these two things. All right, so great. Right, we have two indicators. So what can we do now? Now this is a common cause. Right, so this commonly causes both the first and the second variable. So these might be two questions, right? So this might be depression, and y1 might be sadness, and y2 might be concentration problems or worry, for example. How many observations do we have now? So we observe a covariance matrix with a, let's draw it a bit bigger. We observe a covariance matrix with a variance of the first variable, a variance of the second variable, and a covariance between the two. So 3 observations. How many parameters do we have? 1, 2, 3, 4. So 4 parameters. So we still have degrees of freedom of -1. Right, so we still cannot estimate this model. We still don't have good degrees of freedom. So all nice and good, but it's still not something we can actually use in practice. All right, so let's try to make it bigger. All right, so now we have 3 indicators. So how many pieces of observations do we have now? We only look at the covariances. We don't look at the means because we ignore them in this set of slides. So we have a variance for y1, a variance for y2, a variance for y3, a covariance between y1 and 2, a covariance between y1 and 3, and a covariance between y2 and 3. So 6 pieces of information. Right. How many parameters do we have? 1, 2, 3, 4, 5, 6. Degrees of freedom equals 0. Is that bad? No, that is good. It means that the model is identified and we can actually estimate these parameters. In essence, it means that we have 6 equations, an equation for every variance and every covariance. We're trying to solve that. You don't have to do that, right? The computer will do it for you. We have 6 unknowns, 6 knowns, so we can get those estimates, which is nice. We can get this vector loading, we can get a standard error on it, we get significance values, things like that. It's not great though, because this model will always fit perfect, which means it can reproduce the covariance matrix exactly. So we can't really say, is this a good model or not, because it is a perfect model, because it will give you exactly the right result. That's what you get with degrees of freedom equals 0. Like in a regression model, let's say if I have like a degrees of freedom 0 would look like this, like a line that predicts every point perfectly. All right, are there any questions so far?
Just one came in chat. Adding more data points is less important than number of variables. That is, sample size is less important than DVs, in other words.
Yeah, so, well, adding variables will lead to an estimable model. All right, so they do something different. So if you add people, you'll get more precise estimates, which is important, right? So if you have only 10 people, your estimates are really imprecise. You have very big standard errors. So okay, sure, you get something, but you can't really make a robust claim about that. It's not really generalizable. But so you want to add more people because of that. But by adding variables, the more variables you add, if you just have a very simple model with like one latent variable causing everything, relatively it becomes more parsimonious. You get more degrees of freedom. So that means that you can have a stricter theory to test, which is a nice thing. Right? So the more variables you add, the more complex your model can be. You can add more things, and yeah, the more well defined your model is. So they're different things. Right? It's not like you don't want to add people. You want to have a high sample size to get good estimates. And the number of variables, not like if you add 100 variables, it becomes a bit hard to compute things, and you might get a bad fitting model because somewhere in the 100 variables things are not going well. But if you do get a good fitting model, then that's a really, really, really powerful model, which would be interesting. That makes sense? So the variance of the latent variable you do well, actually the variance is constrained to 1. So you're not actually estimating the variance, you're estimating the impact the latent variable has. So you're estimating the so really you're not interested as much in the variance of a latent variable. You're interested in, for example, the correlation between two latent variables, or the regression between two latent variables, or the mean difference between two latent variables. Or if you have two groups, then the difference between variances. That's the stuff you're interested in. You need to have more sample size to get more precise answers there. And knowledge of talking to less people, but talking to them longer, so basically helps in setting more. That's a nice way to frame it. And statistically, adding variables is actually also adding data points. You can model a Gaussian as and for 100 people with one variable also as like one person measured 100 times. It's a weird thing. I won't go into that much detail now. All right. So how do we do all this? You don't have to actually solve for these, right? So this gives me 6 expressions and 6 unknowns, and you can solve that theoretically. You don't actually have to do that. Software will do that for you. So what is happening? I have a matrix with vector loadings. So this might be, for example, 0, 0, 0, 0, 0, 0, a 1 here for constraints, and something that I want to estimate, some latent variable, lambda, some lambda here. I'm terrible at drawing, but I show it better in the next slides. So that includes some parameters you want to estimate. You have their vector variance matrix with the covariances between the latent variables. That's the stuff we're interested in. And we might have ones here as well if we want to do constraints and variances. And we have this theta matrix that contains residual variances. And usually that has a lot of zeros and only things on diagonal. Those things combined, if you know matrix algebra and matrix variance covariance algebra and stuff like that, you will know that that's true. If you don't know it, then just trust me that that's true. Those things combined using matrix multiplication lead to a model for the variance covariance matrix, which you call sigma. And that's really important in structural equation modeling. So when I teach a course on this, I tell students, okay, print out this expression, print out a poster, hang it on your bedroom wall, look at it every day. It's a beautiful expression because basically this tells us this contains all these expressions within the matrix form. So we can only do it once, which is nice. Any SAM software will do this. It will, let's say, start with some starting values. So it will start with the first guess of the parameters, compute sigma, and then put it in this expression in some stepwise algorithm to optimize this fit function. Optimizing meaning that it keeps trying different parameters so that this thing becomes as low as possible. So you call the fit function. And that we use, for example, with some estimator. I actually use the R function NLM-INB for that. That's what Latent used as well, but you can use other estimators as well. So what's happening here? Sigma is this variance coverage matrix we're modeling. S is our observed coverage matrix. If our model is really good, then sigma equals S. It's the same thing. Then this becomes an identity matrix. The sum of that is the number of variables. This thing becomes 0. We subtract number of variables, and then this thing is 0. If sigma is not S, then this thing is bad. Then this thing is higher than 0. That's the idea. So ideally, we have this as close as possible to 0. And yeah, that's how we estimate these parameters. We just optimize, try the best values many times until we get the best possible fit function. This is what we call maximum likelihood estimation. Again, can talk about it very long. I won't do that now, but that's the rough idea that's happening. So any SAM software, you won't have to do this ever yourself, but any SAM software package will have these expressions in there. Somewhere there's this model here, somewhere there's this expression here. And that's basically send this to that, optimize it, right? So try different values and then you get the parameter estimates. Okay, and then you can come up with all kinds of more advanced models and they all use basically the same logic. So here I have a CFA model with 2 latent variables. I have 2 times a factor loading set to 1 for scaling. And other than that, I have factor loading estimating here, factor loading estimating here, a covariance between related variables. That might be what I'm interested in. Like, do these things correlate with each other? Residual variances, and things like that. So I can fit this model. I can see is it a good model or bad model. If it's a good model, then that's very interesting because it tells me that underlying this data set of 6 variables, a model that only assumes that there are 2 common causes that are correlated and nothing else is fitting well. That means that, okay, I assume there is actually something underlying the data that I can measure, right? And I can even test the correlation is 0 or not. I did not include now how you do a structural effect like that. It would include like another matrix called beta. It actually makes this expression a bit more complicated, but it's not that important, not that different actually. And yeah, we can do other things. So for example, we can add residual correlation. So here, that basically means that I'm adding a variance here. What's that mean? It means that I assume that these 2 items, y3 and y4, are correlating more than what I expect due to the linear variable variances, variables alone. Right, so for example, let's say this is depression and this is anxiety, but actually both have a symptom called insomnia. So if I have insomnia in both, I'm going to assume that they're correlating super strongly, more than I can expect with only this covariance. So I can include a residual effect here to model that better, which is pretty cool. I can also make my model more complicated. So for example, I assume this item is actually caused by both. So now let's say that this is insomnia and I just model it as a item that's caused by both latent variables. I can do that as well. It would basically be like a cross-loading here. And you can come up with much more interesting models. So yeah, you can come up with, for example, a model that does like a higher order factor. That would be a structural effect, which I didn't introduce now, but it's the same logic. And if you have these structural effects, you can do other things. You can come up with a model, like for example, if you have 6 measurements, or let's say 3 measurements. Oh, 3 measurements of a variable over time. We can do a longitudinal model where we assume that there's some random effect intercept and a random effect slope, which is called a latent growth curve model. This is a terrible drawing. I won't have time to really go into detail on this, but it's also an interesting thing. It can be some sort of multi-level model on time, for example. And there are really a lot of different models you can come up with and conceive if you have this flexibility in modeling. Now this is what we call CFA, this model here. Any model that has any number of latent variables and any vector structure, so any combination of these matrices. If we add this beta matrix for structural effects, which would be these arrows, then we call it SEM. I'll only talk about CFA now, but basically the logic is the same.
Dr. Epskamp, sorry for interrupting. There's one question.
No problem.
What is the difference between CFA with two latent variables and a structural equation model?
All right, so a structural equation model is actually this, but a little bit broader. There's a effect here where we're also modeling in effect this plus zeta. So the latent variable is some regression on itself with some beta matrix plus zeta. The CFA model is a special case where beta equals 0 and this whole thing drops out. So the CFA model is a SEM model. It's a special case of the SEM model. We call it a CFA model if you have only covariance between latent variables. We call it a SEM model if you also include like a structural effect like that. But basically you can see CFA is SEM. Right, so SEM and then CFA is a subset of that. Well, that's terrible drawing, but that's the idea. The reason why I'm talking about CFA only today is because it's easier, and all the stuff we talk about with fit measures and how to do it in Latent, it's the same. If you do SEM or CFA, it doesn't matter. All right. So let's go. Let's talk about fitting this model. So this is the main idea. So basically, yeah, we estimate these parameters so that this thing is as low as possible. Is FML the fit function, which is proportional to the likelihood. That's where it comes from, if you know that. But how do we know if a model is good? So how do we know if this model is a good model or not? We want to fit the model. Now, a nice thing is that we can do that. We can get significance values out of it. So if you have this FML, we can multiply with the sample size to get something we call a test statistic. Normally, this is just called chi-square. Like the software will just call it chi-square usually, but you can think of it better as a test statistic. This test statistic is chi-square distributed with the same number of degrees of freedom as the model if the variance of y follows sigma. So if sigma is the true variance coverage matrix. That's a weird thing, but sigma is this matrix we constructed by optimizing our model and getting the best possible parameters. And then we know that if that is the true model, then we know what we should see in the sample in terms of variances. So basically what it means is sigma might be, for example, let's say for 3 variables, it might imply the same covariance for between different items. But in our sample, we're going to get something else. We're not going to get the exact same value. We're going to get like 0.12 or 0.09, right? Or there's some sampling variation. In a different sample, we might get something else. In a different sample, we might get something else. We know that if this is the true model, then this chi-square distribution will explain the sampling variation. We'll say, okay, so if this is a true model, t should actually be 0. But it's never going to be exactly 0 because there's some sampling variation. So we know it follows then a chi-square distribution. Now that's a nice thing because it allows us to do hypothesis testing. If we are frequentists, but I'm going to assume we are for now. It allows us to do hypothesis testing. The interesting thing is that the null hypothesis here is the variance is the same, the observed variance in our data, comes from a distribution where the sigma is the true variance. Now this sigma is from our model. So what's the interesting thing here is that we don't want to reject this hypothesis. So sure, we call it a null hypothesis here, but actually this is the hypothesis that we want to keep. If we reject this hypothesis, it means that we see a pattern in the data that is just not in line at all with our best possible estimate of our sigma matrix. How can that happen? For example, here, this might be from a one-factor model where I assume the same covariance between items, but maybe two items are covering very different. Right? There's not at all any reasonable similarity here, for example. So what we can do is we can use this test value to see, okay, is our observed t-score, or observed test score, which we get from this FitML, is it likely under the data or not, under the model or not? And if it's not likely, we can reject the model, which is not something we want to do, right? So we actually want to not reject it. So it means we want it to be above alpha. And so that's a bit different than what we normally do. Normally we want to have a significant model. Now we want to have a non-significant model. And actually the test that we're then doing is testing if our model is not significantly different from a saturated model that explains everything perfectly. That's if you really think about define it in detail. Okay, so what does it look like? This is what this chi-square distribution look like. This is a center point on degrees of freedom. The degrees of freedom come from the model. So basically, this chi-square test statistic, so this n times the fit function, will follow this curve if the model is true. But let's say we observe this test statistic. So then this area indicates the p-value. It's very low. So then we would reject the test statistic, or we reject the model. So then we would say the model does not fit the data. This is, for example, the degree of freedom is 24 and the test statistic is 50. Now let's say here, the test statistic is instead 30. The chi-square test we get, the p-value is above 0.05. So then we could say that the model fits the data. So in this case, the p-value is much larger. We don't reject the model, which is a good thing. That's what we call testing for exact fit. Which means we really test the hypothesis that our data is exactly from the distribution with this sigma. All right, so we can do this, and on theory this is very nice, and this is what you should always report if you do a SEM model or CFA model. This should always be reported. But in practice, you'll get output like this. Like Latent, which is the function we use, latent variable analysis. Latent ran 301 observations. Those are the people in the data actually. Degrees of freedom of 24 with 21 parameters. All right, we get a test statistic of 85, so that's the chi-square. And the p-value is pretty much 0, right? Like it's not actually 0, but like very, very low. The model does not fit. Now, this is something that you basically almost always get at high sample size. Right, so in this case, 300 is already quite relatively high for this. Now, why is that the case? It's pretty strict to really assume that the model is exactly true. Right, so let's say if you have this model here, it's a really strong hypothesis not to assume that there's nothing happening here, or nothing happening here, or nothing like some other latent variable influencing things or stuff like that. Very strict. Right, so we kind of already know that the model is wrong. Right, and if you're going to collect data, at some point you're going to see that. It's the same as trying to test for normality. And you do like a Kolmogorov-Smirnov test, and then you get a significant effect. Sure, okay, nothing is actually normal, but normal is still a pretty good approximation. So the true model might not be exactly the same, but it might actually be nearly the same or nearly enough the same. So, but yeah, and still, if the sample size goes up, we will almost always expect to reject the null hypothesis. So sure, the chi-square test is nice. It allows us to test the model, exact fit. We should report it, but at the same time, we should expect that it's going to be significant, so that we reject it. Are there any
We have a
questions so
new
far?
question.
Yes.
Yeah, we have one.
I have a model with ordinal items. I read it. The best estimator for ordinal data is the weighted least squares mean value adjusted, I think. The model shows great fit. If I choose ML, the model fit is not good. RMCA, which I'll talk about in a bit. I am somewhat confused about what is true now. Is my model good or not? This is more about violations of normality. So I am going to talk about if you assume normality. If you have ordinal data, which is really a big topic by itself, and I won't have time to really talk about that, then the likelihood expression, so this expression, this comes from the normal likelihood. The likelihood means how likely it is that you observe your data given your model. That assumes the normal distribution. The moment you have ordinal data, then that's not true. It's not a normal distribution because it's discrete. Now, usually for five observations or so, if it's like discrete enough, I actually think it's fine, but it really depends on what type of ordinal data you have, right? If you have 3 levels and the histogram looks like that, it's hard. If you have 4 levels and it looks like that, it's already much more reasonable to have a normal approximation. Now, in this case, yeah, the more appropriate thing to do would be the weighted least squares mean value thing, estimator. So then, yeah, that RMSA might be more trustworthy, right? But it's also problematic. Like if you have a low sample size, then actually the handling ordinal data sometimes works poorer than treating the data as continuous. It is a bit questionable. It doesn't necessarily mean that one of them is true and the other one is not true. But technically, the maximum likely estimator then is wrong. But yeah, it might still be a good approximation. So this is really, yeah, quite a tricky thing. I would probably look at more if it's sample size, what are the levels. If you have like a large number of levels, like 7, I would just use continuous maximum likely estimator. You can use robust estimator, for example, if you assume there's no normality. If you have high sample size, I would use the weighted least squares method, but if you have low sample size, I wouldn't use it. That's my recommendation on that. But yeah, there's really quite a lot to say about that, so that's a hard question to answer. All right. So we're rejecting exact fit. We have a significant chi-square test. Is that a problem? Not necessarily. So it might be that the model is wrong, but it's still useful. And for this reason, there are a lot of fit indices that have been posted in the SEM literature to get an idea of if the model is still good or not. And all these fit indices are numbers we can interpret, and they try to tell us, okay, the model might not be exactly right, but it's still extremely useful. So we have our model. What these fit indices do is they try to compare this model to 2 different types of model. The saturated model, which fits perfect. So here we just have a covariance between every item, so it reproduces every correlation perfectly. Or a baseline model where we don't have any covariances, so we're just assuming that the covariances are all 0, which is a stupid model, but it's the most simple model we can come up with. So what we want to see is that this is about equal to the saturated model, roughly in the same area. It doesn't perform that much worse, and it will perform worse if it's significant, but not that much worse. And we should see it much better than this baseline model. And that's the idea of many of these fit indices. They compare this t-value, this test statistic, to this model, saturated test statistic, which will be 0, or the baseline one. Okay. And there are a lot of these things. So I'm just going to show a few, but really there's like decades worth of literature on new fit indices. There are new developments in that as well. Well, dynamic fit indices, where you try to get like recommendations of the values the cutoffs to use per dataset. I won't go into that detail. I just want to give you some introduction to this. The first one that most people use is the root mean square error of approximation. Basically, what this does, it is scales this test statistic, this chi-square test statistic, to a more interpretable scale. So this thing, the chi-square distribution has a center point around 2 degrees of freedom. It will usually be above the degrees of freedom. So if it's below the degrees of freedom, it will always fit well. So then we don't actually need to use RMCA because the p-value will already be non-significant. So this is very simple. It just does minus degrees of freedom and will be 0. It says it is a negative, it will put a 0 because we can't do a square root of a negative thing. And then scale that by the degrees of freedom. That's really all it does. And then take a square root, because why not? We're talking about variances. It's easy to put a square root in there. That gives us a scale, something that is above 0. And it's it's independent of the number of variables used, because we scale by the degrees of freedom, which is nice. And it has some interpretation. There are many different recommendations there, but typically less than 0.05 definitely is considered very good fit. Above 0.10 is definitely considered very poor fit. Mostly people will say already above 0.08 is considered poor fit, but definitely above 0.10 is bad, below 0.05 is good. In that area, 0.05, 0.08, it's like, yeah, it's fair, it's good, it's mediocre, it can still be considered good. It's a bit more arbitrary, but that's mostly the interpretation. Below 0.08, people would say it's still an okay model, usually. That's the RMSEA. So the RMSEA is basically a scaled version of the chi-square. There's a nice thing about the RMSEA that I don't talk about here, but it has a sampling distribution, which you can use for power analysis. So that means you can use this actually to determine sample size. But it's a bit more of a complicated topic, so I don't talk about it here. Then other fit indices are incremental fit indices. And so this model actually compares to the set fit model, this fit index. The incremental indices compare a model to the baseline model. So this is a model where we don't have any covariances. It's a very simple model. Every item is a variance, and there's no covariance between them. So the moment we see any correlation in the data, we know this model is wrong. But if we want to see, okay, so our model is implying some correlations, is it working better than this baseline model? Much better, ideally. Right, so the true model might be here. The baseline model is bad. We want our model to be really, really good. That's the idea. So all of these, basically, they are from 0 to 1. Some can be above 1, but interpretation usually above 0 and 1, between 0 and 1. And we want this value to be high, typically above 0.90 or so. And there are a lot of these things that have been proposed. They're all some way of having this test statistic, chi-square test statistic from the baseline model and the model, and then some way of scaling it. So this one scales with degrees of freedom, this one does not, this one does some other way of scaling with degrees of freedom, this one only uses the model degrees of freedom, this one uses the baseline degrees of freedom, blah, 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 blah. There are many different ways in which these have been defined. And they're all called something I, like NFI, TLI, RFI, IFI, RNI, CFI, and there are way more of these. They all actually have their own exact cutoff, and then you can also do dynamic cutoffs now. But typically, basically, just above 0.95 is really good, and above 0.90 is acceptable fit. That's roughly the interpretation of almost all of them. With very few exceptions. So usually people report the CFI, TLI, and NFI But you can get all these measures and you can also report them all, and they can all be insightful. Usually they will be very strongly aligned. Like it's very rare to see that one is indicating bad fit where others are indicating good fit. But if that happens, it might be interesting to see, okay, what's actually happening in that one index, and then maybe read literature. Okay, when is that going wrong? Is that something to worry about or not? So it's good to look at all of them, but they basically have this same interpretation of higher should be better. Then the last fit index I want to talk about is the goodness of fit index, or the adjusted goodness of fit index. Again, an I, but it's not incremental fit index. This is basically analysis to R squared, or how much variance is explained. So this really looks at, okay, how close is my S matrix to the sigma matrix? How much of the variance am I actually explaining? Again, above 0.90 is good, but it doesn't compare to a baseline model, so it's not an incremental fit index, but its interpretation otherwise is similar in terms of what's good fit or bad fit. Now that's quite a lot that you can get out of the data, and often in a SEM paper you'll see this. So in a SEM paper you'll see, all right, the model, a path diagram like that, the test for chi-square, now this one here, and then a bunch of these fit indexes reported as well. That's very common. So you always want to report the chi-square test statistic. Why? Because it's used in all these things, right? So this is chi-square test statistic, this is chi-square test statistic. Here it is, right? It's used all the time. So that's why I always want to report it, because it's a thing that's pretty important if you want to recalculate anything. You want to report several instances. Don't cherry pick the ones that make your model look good, right? Just report anything. You can report as many as you want, but it might be that some fit instances just work really badly in your specific setting, right? So if you have one that is really bad, maybe you want to look that up if that's like actually worth reporting or not. It might just be that that one is not actually intended to fit well in a particular setting. That could happen. So report several, but I would usually at least report RMCA, CFI, RNI, TLI, for example. This I did not talk about, but it's something you can do. And yeah, try to make a holistic judgment. So basically, okay, try to take all this information into account. Is your model good or not? Usually it will align, but it can happen, for example, that RMSCA is indicating good fit, where the incremental fit is indicating bad fit. In that case, the model is pretty okay. It works similar to the baseline model, but it's not performing that much better. Sorry, it's similar to the saturated model, but it's not performing that much better to a baseline model, meaning that it's not actually explaining much covariance. Maybe there is not much covariance to begin with in the data. And in that case, okay, our SEM model is nice, but it's not actually doing much more than what we could do with a very simple model. Are there any questions?
There's one. What is the usual case to all fit indices conquer? In which usual case do all fit indices conquer?
What is the usual case to all fitnesses concur? Usually they will align. If a model is bad, you will see it in every way. But it can happen that one fitness is good. Right? It can happen that incremental fitnesses are a bit like all around the cutoff point, like 0.90, 0.89, for example. And it's like, yeah. Okay, most of them are actually indicating acceptable fit. But yeah, one thing I see often is more that RMCA is good, but incremental fitnesses are bad, indicating that the baseline model is just performing better. But yeah, there actually is an interesting paper about it recently. I don't have the others at mind now, but that showed the interpretation can actually be quite complicated if these things are not aligning. But often it will be the case that they align. Any other questions?
What if there is a disparity, then what could be the rule of thumb of solving it?
There's not really any rule of thumb. Like if your RMSA is good and your CFI is bad, you're not going to say, okay, I'm going to pick the RMSA and forget about the CFI. Then you shouldn't look at the CFI to begin with, right? So you really want to try to figure out why that's the case. And you might want to adjust your model to get a better model then. That's not really the case that, okay, yeah, if they're not aligning, then you can just say, okay, I do that. It's a hard question.
There's another question I think that was missed. Are cross loadings an acceptable thing or should they be avoided?
So cross-loading can be included in the model, which is a nice thing. So normally you have a simple structure, but if your fit is bad, you might see, okay, yeah, there's actually a cross-loading I should add here, and it makes theoretical sense to do so, right? Or you might have a scale in mind that has a cross-loading in there. That's not a bad thing at all. I mean, if you have like insomnia and it's like indicating both latent variables, yeah, sure, you can include it as a cross-loading. That's not a problem. There's actually a nice thing on CFA that you can do that, because yeah, if you just take some scores, you can't take that into account. All right. So I only have some slides left. I think I'll skip sample size and then I'll just go through the code. I want to quickly talk about model comparison because that's quite an important topic. So let's say we have two models, a model here on the left and a model here on the right. And one thing we can see here is that this model on the left is nested in the model on the right, meaning that there's a parameter here that is 0 in this model, but it's not 0 here. So if this model has this parameter set to 0, it becomes the same model. Now, how do we know that including this parameter was a good thing to do? So maybe what we get is we get a bad fit here. We try to add this parameter, and we're going to see, okay, was it worth it? Did it improve the fit? So that's model comparison. Now that's a whole topic as well. I'll just be very brief about it. There are multiple ways to do that. If you have two models, you can estimate their AIC and BIC and pick the one that's lowest because that's the one that's better. That's the idea of an information criterion. But you can also do a significance test. If the models are nested like this, you can do a significance test between the two models, which is a pretty nice thing to do. Now that significance test is called a likelihood ratio test. And the idea is pretty straightforward. The difference between the two chi-square tests is also chi-square distributed, with the difference between the degrees of freedom as the degrees of freedom. So that means that we can get a p-value out of a difference score. And we can run the test, is the difference 0? If the difference is not 0, then you would get a significant result. If the difference is 0, then you would not get a significant result 95% of the times. Right? That's the main idea. So that's a very useful thing to do. We can just run a chi-square test to test if a nested model is significantly different from a non-nested model. Another thing we can do, and you can do this for non-nested models as well, is look at the difference between the AIC and the BIC. Basically, both are measures that measure the fit of the model, the likelihood, with some penalty for model complexity. Meaning that, okay, you want to have a model that fits better, like this should be lower, but I'm also adding parameters that increases this, so that balances these two things. Usually lower is better. So if we compare two models, we can look at which one is lower AIC or BIC. The BIC tends to be a bit more conservative. It has a more stronger penalty on the parameters. Q is here the number of parameters, which means that it will tend to prefer harmonious models than the AIC. So they might not align. And yeah, that's again something that you need to take a holistic adjustment on. There's not really any rule of thumb that says that one is really better than another. That really depends on the setting, You can do simulation studies on that. So sometimes the BSE is, it's conservative, so you're more careful, but you might miss out on effects. So you might miss per power, and there's a trade-off there. Now, there is a really nice thing in SEM, and a very important thing to mention, and those are modification indices. Modification indices are values that it's amazing that you can actually compute them. You can take a model, like this model here, and if it fits bad, you can look at the modification indices, and it will tell me if I add this parameter here, the model will improve. It's amazing that you can calculate these things mathematically, because you can just use the model and you get information about all the possible parameters that you can add. So that's a really, really powerful thing. So it allows us to see, okay, a model fits bad. What parameter can I include? Maybe there's a cross-loading I can include. Maybe there's a residual correlation I can include, something like that. Then I can try to adjust my model. So maybe, okay, so maybe we had this one fitted bad, but the modification index tell me that if I add this one, the fit will improve. So maybe I want to see if that will work well, and then see if the model fits better. I can do that, and it can be useful because it's useful to have a good model if you want to do, like, for example, hypothesis testing on then the correlations. You want to have a good fitting model first. There's just one problem with it, that you should always treat this as exploratory research. So that means that the moment you start adjusting your model, you have a model in mind, right? You tested it. The moment you start looking at the modifications, this means you look at the data in a way, you change the model, then it does mean that your model is no longer confirmatory. That is fine, right? If you mention it in your paper and you say, okay, so I use modification indices and I changed the model, and like modification indices suggested that there was a cross-loading, and then I looked at that variable, and yeah, sure, it was insomnia, and it was in both depression and anxiety, so it made sense to include that, so I did that, and the model fit improved. Okay, I have a better model, and then I use that for my hypothesis testing. That's all fine, but you shouldn't pretend that then that was your confirmatory theory all along. That's a pretty big topic in SEM, because sometimes you'll see in the literature, let's say a model like this reported, where you have some weird cross-loading there, or some weird correlation, something else, and then the authors will pretend that was their model all along to begin with, and you don't know for sure. But yeah, if there's there's some weird stuff happening there, it is quite often the case that it is added because of modification indices. Right, so if you look at modification indices to modify a model to get a better fitting model, because your model is bad before, and you want a better fitting model to do something with it still. But if you're really hardcore on confirmatory fitting, you would just say, okay, I've tried to fit this model, gather data, no good, yeah, gone, new data set. Right, but you might want to use your data still, so it's not bad to modify the model so you can do something still, but you should report it. That's the main idea. And that's an important thing to know also when you read SEM studies. Okay, then I think I'll skip the section on sample size. It is quite hard. The thing is that, yeah, if you do power analysis for ANOVA, for example, you need to have an effect size in mind. But now the effect size are all these parameters. You need to have some idea about these parameters, and it really depends on what your sample size should be, depending on those parameters. So it's quite hard to say. There's some general guidelines, like about 200 people at least, or 5 to 10 per parameter, or 100 to 200 people minimum. Some general guidelines, some rough guidelines, but usually, yeah, it's really hard to say. It really depends on what you want to do. But there's a nice paper. I'll just show the link to the paper. There's a nice paper where there's a Shiny application that allows you to simulate data, which is quite nice. Where you say, for example, okay, I have a model in mind, like let's say this model here. I have a model in mind. And what are you actually interested in? Right? Why are you fitting this model? Okay, just to show that there's two latent variables underlying data. Okay, sure, but maybe you're interested in a certain parameter, like this correlation. So you want the power on that parameter. All that you can get through simulations if you have an idea about all these other parameters. But if you put something in, then you can simulate data and try to get the power of a certain parameter. There's a nice application that allows you to do that, which is really nice and useful as well. All right. Any other questions so far? Can indicators be directly correlated, or should they only be correlated to the residuals? In SEM, we have exogenous variables and endogenous variables. And exogenous variables has no incoming arrows, and endogenous variables has incoming arrows. The exogenous variables, right? So exogenous, endogenous. Any endogenous variable, we're modeling the variance, which means that it does not have a variance by itself. So this thing has a variance by itself, and the endogenous variable has a residual variance. And that means it also cannot have a covariance by itself. It always has a residual covariance because we're trying to model the variable. The moment you add something that is part of the variable, you're not modeling it anymore, so it's complicated. So indeed, in SEM, the indicators cannot be directly correlated. They always are either residually correlated or correlated to the latent variable. Does that answer your question? All right. So then, yeah, that's really what I wanted to tell you to introduce SEM. It's really like going very fast through it, but that's the main idea. Like we try to form a model like this, well, like this here. We try to fit it to data. Basically, if we're fitting it, then our model is trying to reproduce the covariance structure. That's what it's doing. We're estimating the model parameters by trying to get the covariance structure as close as possible to the observed one. Then we try to look for the fit measures. Is it actually a good fit? Is the covariance model actually reproduced or not? If it's not, we try to do it with approximate fit measures to get an idea if it's still okay. We might want to adjust the model, or we might want to compare the model to different model or competing models if we want to. And that's already like getting really far into what you can do with CFA modeling. Right, in the paper you'll see it will have a path diagram like that, it will have a chi-square test, it will have fit measures. If you want to take it more advanced, then you include structural effects or measurement variance testing, where you can compare multiple groups with each other and do tests like are their mean levels different. So one thing I can do is I have a latent variable model in two groups, and then the mean becomes identified in one group compared to the other. So I can say, okay, is the mean level of the latent variable different in one group compared to the other? It allows you to really test this hypothesis on the latent variable level. Okay, I have group 1, there's a distribution here, and group 2 maybe here. So there is a significant difference between means at the latent level. One group is more depressed than others, for example. That's a super powerful thing, and that's a bit more of an advanced application of SEM. We can also use it then to model things like longitudinal data, and yeah. But this is really the core of it, right? The path diagrams, the fit measures, comparison, things like that. So are there any questions on this? Otherwise, I'll go to the code.
I don't see any other questions in chat.
All right. So in this set of slides, I have some explanation of the code. I'll skip that because I had the same explanation in R. So this is included this, so you have all the stuff also in the slides. So I want to go to an example. So this is an example. So I teach a course on SEM. I've been doing it for a while. And when I used to teach this in Amsterdam, I asked students to gather data. So what I want the students to do is to form a SEM model, think of questions themselves on how items are related to each other, and then fit it to data. So they had to come up with like some SEM model, some CFA model, gather data, right, on Twitter, for example, or with their friends or family, fit the model, and then the learning experience was usually that the model doesn't fit, right, which is good, but always some people would have a good fitting model. So this group did that. They had a questionnaire that they came up with themselves to measure Star Wars fandom. So there were 10 questions. The first one was, I am a huge Star Wars fan. Right, I'll zoom in a bit. I'm a huge Star Wars fan. The second one was like, I would trust this person with my democracy. I enjoyed the story of Anakin's early life, things like that. Now, the idea that they had was to measure the 3 trilogies of Star Wars. Now, I'm going to assume here that most people know Star Wars, but just to clarify, Star Wars had 3 trilogies. This first one is the original one, came out in the 80s or so. Oh, sorry. Can you still hear me? I think I put up my microphone. Right, the
Yeah, I
original.
can hear
Yeah,
you.
okay, great. The original trilogy is really good. It came out quite some time ago. Then at some point in the early 2000s, there was this prequel trilogy, which many people hated because it had Jar Jar Binks, but it also had really flashy lightsaber duels and like this super cool thing with the dual-sided lightsaber. I really loved them because I was a child back then. And then recently, you had this sequel trilogy that came out where we had new movies. Important to note that this data was collected somewhere here. So this movie wasn't out. And this movie was very recently out, so didn't really impact the data that much. So it was mostly this movie. That's important because these are just terrible. Like they're really terrible movies, in my opinion. But this one was pretty good, and it was basically just very nostalgia based on this original trilogy. Okay, so what they tried to measure was for every item, every trilogy, they had 3 items measuring how well people like them. And this I'm a huge Star Wars fan was assumed to be related to all 3. And this is the final model. This is included because of modification index, but I'll show it in a bit as well. So I had this one item indicated for all 3, and then 3 indicators here, 3 indicators here, 3 indicators here. Okay, so I put this data on Open Science Framework, this link here. I think the link should be sent around. I'll put it in the chat as well. Oh. This link here. But I'll just quickly show the code. So that's here in R. This is what my R looks like. I'll have 2 things that are different from you. I go here to pane layout to set it like this. Console and source here. I like this theme. I like this because then I'm not competing for vertical space. I also have now, I probably didn't put it off, GitHub Copilot for AI recommendations. So say hi. And then I get like AI recommendation for text. That's pretty useful. Yeah. All right, set working directory to source file location. It sets the working directory to the right file. Then I can read this file into R, which has the data. Let's take a look at that. Looks like this. So I have questions and people. 271 items. We sent it around on Twitter and stuff. That was quite nice. Got a lot of responses. These are the questions. And then we can model that using Latent. Now there's a hard way to do it. There's an easy way to do it. This is the hard way. I want to include it so to show how to model the exact thing. So here I set the vector variances to 1. So this thing is a variance or covariance. And this is a vector loading. But you actually don't have to do any of this because you can do it much easier with this syntax here, the CFA function. But if you want to see the more detailed form of how to do a model like fully, like you have to specify all residual variances, then that's like this. But let's skip this, keep it simple. So here I have the model. So this says, this thing says is indicated by. So you see that this is a similar syntax to like LM and R, but we have to specify it as a character because of a more detailed model. This is indicated by, so this defines latent variable. I define a pre-clause latent variable and says is indicated by this indicator and this indicator and this indicator and this indicator. I define a original trilogy is indicated by this one. This is the same one. And because of that, I set the variances to 1 rather than the vector loadings, because the first vector loading is the same, which is this argument here. So I have the original trilogy with these 4 items in the sequels. So I run this model. Then I have CFA. I just give it the model, the data. This sets the latent variable variances to 1. Normally the first vector loading is set to 1, which is fine, but in this case it actually leads to problems because, well, I'll show it in a bit. Okay, then I get the fit. I get here my chi-square test statistic. And this was great. So I told you, like, my learning goal was that you think of a model, you pre-register it, you get data, it doesn't fit. But they actually got like exact fit. So they got a p-value that was not significant on a huge sample size, 271, which was, I mean, quite remarkable. They have 30 degrees of freedom here, which is not low. So this is really remarkable that they got exact fit. Right, so that was really nice. Then this function here says we can actually look at the fit measures as well. We don't have to in this case because the model fits perfect, but we can do it. But it would be fit. Sorry, fit measures is the function. And I get all this stuff like RMCA, RNI, NFI, TLI, RFI, CFI, all this stuff. Right. Lots of information. I look at the parameter estimates with this function here. And I get this nice table with all the estimates. The one thing I see here, for example, is that this first vector loading was not really significant for the prequels or for the sequels. So that's this item, I'm a huge Star Wars fan. It was only really significant for the original trilogy, which is quite interesting. So that thing, I'm a huge Star Wars fan, really only measures if you're a huge Star Wars fan at the original trilogy. These are the residual variances. They're not that interesting. The main thing you're interested in here are these vector loadings, see what are the good indicators, and these covariances. I can do standardized equals true. You get some standardized measures. STD all here means what would the parameter have been if the variables were standardized. It means that all the variances were 1. That makes these things the correlations, which are a bit more interpretable. They already were the correlations because we set the vector variances to 1, but that is a bit easier to interpret. So we see here significant correlations, but mostly very strong correlations between originals and sequels, like a super strong correlation. Makes sense because this is what I said, right? It's only the first The Force Awakens movie, which is based as a remake of the original trilogy with flashy effects. So that makes sense. And also a very strong correlation between prequels and sequels. Also made quite some sense to me because, they're flashy effects. Like this correlation is actually quite weak between the prequels and originals, which makes sense because, people don't really like them that much. I think there's a different group of people that like the originals and the prequels. Okay, this is what modification indices look like. So this tells me adding this residual correlation would improve the fit by 9 points, chi-square, which would be significant. And I would expect then to get a value of minus 0.2. So I just showed that you can do this. And you can compare the fit, just to show that you can compare two models with this ANOVA function. And that gives me a nice overview of the difference in degrees of freedom between the two models. This chi-square difference, which is significant in this case, and also the AIC and the BIC. which is useful if you want to compare different models. Now, one nice thing about SEM is that you don't actually need to use the raw data. So here I have the raw data, but you can actually fit the model with just using the sample covariance matrix, which is pretty cool. So here I have only the sample covariance matrix, which I can include as an appendix in my paper. And I can reproduce the exact same model. You'll see here the model is the exact same. So that before, which is nice. So we don't need to send the raw data. I can just do this with the summary statistics of the data. Now, final thing I want to show is I actually wrote a package once. It's already quite some time ago, but I wrote a package that makes path diagrams. And with that package, you can make some diagrams. For example, like this. So you can put the fit object here and then say here standardized. I want the paths to be standardized, which is nice because then so this is the vector loadings, and then include labels of the estimates. And here to show like how you can make it much more fancy. Like for example, a diagram like that. So this is not really intended to be a publishable diagram to show the model that you want to do. That should be something that you make beforehand. It's intended as a visualization of results. So here I see there's a negative vector loading here. On Q4, the special effects in the scene were awful. So there was a negative rate item, so it makes sense. And you see here that this item 1, I'm a huge Star Wars fan, has very weak loadings from the other vectors, so only really a strong loading from the original trilogy. So that's a nice thing that you can do to get a bit of idea. Okay, did I specify the right model? And what did I specify? And some other things you can do here, but it's not that important. All right. Are there any questions?
I don't see anything in chat. I think we can let people unmute if they want now. Do you have more things to go over before?
No, that's basically all I wanted to say.
Okay, great. Thank you so much for that wonderful workshop, especially the comprehensive slides and the R code that you presented. You really took such a complex topic and like made it like digestible. So thank you so much. And I think we can. Do you think we have time for some Q&A?
Yes, sure, of course.
Okay, so if anyone wants to just unmute or turn on their camera, you can just raise your hand. So we will just allow you to unmute then. Okay, I don't see anyone raising their hands. There's one question in chat. What are some checks before performing SEM on data?
The main assumption is normality, but it's also pretty hard to really check that because the statistics like multivariate normality is really hard to check. You can look at the histograms, for example, get an idea if your distributions are okay. You might want to look at the correlation patterns to see if you actually have correlations between your variables, which you are modeling. Otherwise, you're not going to be able to model it. Those would be the main things, I think. Just make sure that there is variance and covariance that you are modeling. And for example, you might have a continuous scale, but everybody scored as 0. That might be a problem. So those are things you might want to check. And missing data, of course. I didn't talk about missing data, but if you have missing data, you want to know why are you having missing data? Like how severe is the problem? What variables are missing? If that's not missing at random, it's an issue. If it's missing at random, you can handle it easily in SEM. If it's not missing at random, that means that people did not respond to questions they did not like responding to, for example, then it's bit more of an issue.
They have also asked how about Z scores.
Sorry, I didn't catch that.
They are asking how about Z scores for.
Um, Z-scores are not that important. I mean outliers, maybe. So the outliers would be violation of normality. So yeah, if you have very strong outliers, that might be something you want to look at as well. But yeah, but that just falls under normality as well. I would be hesitant to really remove data unless you have like really strong outliers, and in general, using Z-scores to remove outliers is also not recommended. But yeah, that might be something to look at, sure. Yeah.
I think that's it. I don't see any other questions. Okay, I think we can wrap up then. Nobody else is raising their hand or putting any questions. Um, so thank you so much, Dr. Epskamp, for doing this for us, and especially at such an odd hour for you. We really appreciate this, and this was an amazing workshop. SEM is something that I personally have been wanting to learn for a long time, and I think this workshop was a really good introduction to it. So, yeah, thank you so much. And thank you everyone for joining us. And we will be sending email with all the resources and also the website and YouTube link for Dr. Epskamp's YouTube channel and his website. So, yeah, thank you so much.
Thank you very much. And yeah, have a good evening, everybody.
You too.
Thank you.
All right.
Goodbye.
Goodbye. I'll end this meeting now.
Right. Okay.